Good evening and welcome to Lowell Observatory's year-long celebration of the 10th anniversary of our Lowell Discovery Telescope. This telescope is the fifth largest in the continental US and one of the most versatile in the world. And throughout the year, every month we're talking about different aspects of the telescope and the research that we're doing with it. In July, we're actually going to also cover the resurfacing of the main mirror, which is a pretty fabulous thing to watch. So we're really excited to talk about LDT, the Lowell Discovery Telescope, and celebrate it this year. It's 10 years of operation, and we've had so many great discoveries and look forward to so many more. My name is Kevin Schindler, and I'm the Historian and Public Information Officer here at Lowell Observatory. And for the next hour, it's my honor to be able to work with three astronomers who have used the LDT. And when we say LDT, that's what we're talking about, Lowell Discovery Telescope. So over the next hour, we're going to talk about small bodies. Every month, we're talking about a different area of research with the telescope. Tonight, we're going to talk about small bodies. We think of those especially as things like asteroids and comets. Joining us tonight is really an all-star lineup that we're really pleased to have. Dr. Nick Moskowitz arrived at Lowell Observatory in 2012 as a postdoctoral fellow, and today he's a planetary astronomer here at the observatory. Dr. Matthew Knight was a postdoctoral fellow and then researcher at Lowell from 2008 to 2015. He's now an assistant professor in the physics department at the U.S. Naval Academy in Annapolis. And Dr. Annika Gustafsson was graduate research assistant at Lowell from 2017 to 2021. She's a freshly minted PhD and is now a postdoctoral researcher at the Southwest Research Institute in Boulder, Colorado. So thanks everybody. Thanks you all for joining us tonight. And we'll get started. First of all, like I said, we're going to talk about small bodies here. So I'll ask each of you to just briefly talk about how you've used the LDT, whether it was for research or commissioning an instrument, and what that means to commission an instrument. And then we'll get into some specific research projects that you've been involved with. So Annika, you're the first one in my screen, so why don't you start off?
Okay, perfect. So as you mentioned, I was a graduate student at Lowell and Northern Arizona University. And so part of my dissertation work was to work on the NITES instrument. And we'll talk more about that as we go along here. But NITES is a near-infrared spectrograph. And so I was one of the commissioning scientists for the instrument, working with Nick. And essentially what we did was put the instrument on sky, learn to take images with the instrument, collect photons by looking at stars and other objects as we progressed. And I worked also on a GUI, which I can talk a little bit more as well, but creating a user interface for the users of the LDT to be able to use the instrument efficiently and move the telescope and take images and so on. And so as part of that commissioning of the instrument, I also got involved with some asteroid projects as well as some comet projects, and we could talk more about those as well. Pretty much all using the NITES instrument as well as some of the other LDT instruments.
Okay, great, thanks. Nick?
Sure, thanks, Kevin. Pleasure to be here this evening. So I've used LDT for a variety of use cases, and as Annika just said, we'll get into a bunch of those, but my primary research interests are in the small bodies of the solar system, so essentially anything smaller than a satellite, planetary satellite, are the types of things that I would study. Near-Earth asteroids, main belt asteroids, comets, TNOs, trans-Neptunian objects out by Pluto. So I've pointed the telescope and studied all of those at some level or another. My most active research projects these days are focused on near-Earth objects. And so these are asteroids that come close to the Earth. We have a number of fundamental questions about that population and what they are. We're interested in studying them from the perspective of planetary defense, which is an endeavor to understand the population of impactors out there in the solar system and the probability of them impacting the Earth and what their properties are so that we can effectively assess whether or not a given object is hazardous to the Earth. Near-Earth objects are additionally interesting from the perspective of spacecraft accessibility. Some near-Earth asteroids are actually easier to get to in terms of the amount of fuel needed for a rocket than the moon. And so these are highly favorable spacecraft targets, whether it's a rover landing on the surface or thinking about future missions to perhaps send astronauts to explore an asteroid. We're studying that population of objects to better understand what the distribution and properties are so that we can better inform future mission activities. And then lastly, NEOs, near-Earth objects, are interesting from a fundamental science perspective. We know that NEOs are coming to us from all over the solar system. They originate primarily in the main asteroid belt between Mars and Jupiter, but we also have NEOs that are what we think of as sort of evolved comets. Some of them are dead comets, so things that once were active but no longer are active. And so because these things are coming to close proximity to the Earth, we can study them in far greater detail than we would if they were in their sort of original home populations before they entered the near-Earth object population. So anyways, that's sort of a very quick overview of some of the stuff that we're doing. And as we said, we'll get into some more detail on some of the projects later on.
It's a lot of different projects. That's great. Matthew?
So I have studied primarily comets, typically imaging using the Large Monolithic Imager, LMI, occasionally spectroscopy, although that's not usually my thing. So mostly comets, some asteroids, and Nick and Annika and I have all actually worked on at least one project together with that, so we may talk about that more later. But I used it, I'd like to say, the very first official science night, I believe. We observed Comet 10P Temple 2 with Dave Schleicher, and in fact, the old Lowell director, Bob Millis, came out that night with us as well for the first few hours of the night to check it out and see it in action. And as I moved away from Flagstaff, I really relied upon the ability to observe with it remotely as well. So I did a lot of the early testing, along with Stephen Levine. I think he and I are the two big heavy users early on of how do you do this remotely. So I have made quite a bit of use of LDT over the years.
Well, that's great. And something, is worth pointing out here. You're talking about small bodies in the solar system, asteroids and comets and such. And you're continuing a long tradition of research here at the observatory, going back to Percival Lowell's day, looking at comets such as Halley's Comet in 1910. And through the years, astronomers like Ted Bohl, who began here at the observatory looking for near-Earth objects, those that could impact Earth. And you're continuing this research, but escalating it, both with this state-of-the-art instrument and also the collaborations and such. So it's so typical of Lowell Observatory, this continuum of research and research we've been doing for a long time. So this is going to be really fun to talk about some of this. So what we'll do is we'll talk about one of the instruments first, the one that Annika mentioned, the NICE instrument, and some of the work it took to make that happen, what it does and such. And then we'll talk about some asteroid research, and then we'll get into comets a little bit, and then we'll look at some bizarro things that are sort of in between the two. So let's start off with NICE. Annika and Nick, you are both involved with commissioning of that. Maybe just talk about, first of all, what NICE is, what it does, and what do we mean when we say commissioning, and then what kind of research are you doing with it now?
Yeah, I'm just going to punt this one to Nick just to start it, just because he knows a little bit more about kind of how we came across the instrument in the first place and how it got to the state it was. And then when I joined in on the project, where we were able to take it from there.
Sure. So, any instrument project is not something that happens overnight. There's a long buildup of, planning the scope of the instrument and designing what its capabilities are going to be and what is actually, what is the unique niche that it's going to carve out. And I came onto the NICE project sort of midstream, well after a lot of initial design work had been done by Lowell astronomers before me. So Mark Bowie was an astronomer of Lowell for many years who helped conceive some of the capabilities of NICE. And then Henry Rowe was another astronomer of Lowell who took over and really got nights pretty far along in the development stage by the time I took over. And so when I took over as sort of the instrument scientist, or one of the instrument scientists for nights, it was kind of ready to go. It was, let's plug it into the telescope and see what it can do, which is great. That's a great opportunity to come along and have something already built and ready to operate for you. I'll just say briefly that NIGHTS was conceived as a near-infrared spectrograph. That's what Annika said earlier. It's what that means is it's collecting near-infrared wavelengths of light from about 1 micron up to 2.5 microns or so. And we take that light and disperse it into a spectrum, and that can tell us about compositions of things. That's typically the type of work that we're doing. And NIGHTS was conceived specifically to probe the compositions of solar system bodies with a focus on outer solar system surfaces. So icy surfaces like those on Pluto and Kuiper belt objects and things like that, trying to understand what ices are on the surfaces and what abundance and what that says about the formations of these objects. So that's a short overview of NIGHTS as an instrument. I think Annika played perhaps the critical role in seeing the instrument to commissioning and ultimately as part of the suite of facility instruments. So I'll let Annika talk a little bit about what commissioning means and what we did to get the thing working.
Sure. And feel free to jump in whenever you want to add something as well. So I joined the project with Nick, as he said, basically at the state where we were able to plug it into the telescope and point it at the stars and see what came through and go from there. So we learned a lot about the calibration images that are required in order for us to get what we would call reduced images out. And so that involved pointing at calibration lamps where we have specific lines that are identified so that we can match wavelength up to pixel on our science detector. And then we also worked a lot with how to communicate with the telescope system. So as Matthew mentioned, LMI, the Large Monolithic Imager, was one of the first instrument to go on the LDT and be used for science, I believe. And so a lot of that infrastructure was built for LMI and for the other spectrograph, Divini. And so when we took over NIGHTS, we had a basic user interface that was mostly taken from Divini and stripped down. And so then we were able to adopt that for NIGHTS specifically, and communicating with moving the telescope in different directions and how can we take an image on the science detector and also on the acquisition camera, which is what allows us to get the target that we're interested on the slit exactly so that we can get light through our slit. The NIGHTS slit mask is, I think, really unique. It's kind of this jigsaw shape where it has a different slit widths. And so depending on what type of target you want, what type of resolution you want, you may pick a different slit. And so matching those locations up with our user interface was something that took a bit of time, and just trying to maximize what we could get with the instrument and make it very user friendly. If you're coming up to the telescope and it's your first time on the instrument, you basically want the system to flow as easily as possible. And so we created a really nice user manual, and I think I'm a bit biased in that because I wrote it. But I think that so far we've had a lot of different people from the different institutions that are using LDT use NIGHTS for a lot of different science use cases, including small bodies as well as stars and exoplanets. And so we've had a nice wide range of science using the instrument. And so I think it's been going well so far.
Yeah. If I could add one thing to that real quickly, Kevin. Yeah. LDT is an incredibly complicated instrument, right? As a facility, it's a very complicated instrument with literally dozens of subsystems. You know, it's not just a telescope and some gears that move that telescope. There are dozens of subsystems that control everything from cooling of the instruments to the mount, to the support for the mirror, to the dome, weather monitoring. All these things are built in. And when we commissioned NITES and when Annika wrote this user interface for it, it really was figuring out how to create a simple view for the user, the observer, while still being able to communicate with this incredibly complicated set of subsystems that control everything. And so that was an interesting experience for me. I'd never seen sort of under the hood of a telescope at the level that we had to do for NITES. But as a testament to Annika's work in commissioning the instrument, that we got it working in the way we wanted, and that most users, as she says, show up and learn pretty quickly that, you know, this is how I do it. Okay, I click this button, I pull down this menu. Okay, I'm collecting data, I'm doing my science. And that's really what you want for an instrument. You don't want users having to spend 2 nights learning how to use it, but instead quickly get the photons they need and be able to do the science they want to do.
And I think that you brought up a good point about, you know, being efficient with time and being able to make the most of that telescope time. And that gets to one of the important aspects of the LDT, and that's is adaptability and ability to accommodate several instruments at once. Maybe, Nick, you could talk about that a little bit. You've talked about NITES as one instrument, but maybe talk about just briefly the other instruments on the telescope and why the LDT is so powerful with those telescopes.
So like any telescope, LDT focuses light down to a focal plane. But the thing that's really unique about LDT is that our focal plane is populated with a cube. And so the light sort of enters at the top of the cube, and then every other side of the cube has an instrument mounted on it. So that means we can have 5 instruments mounted at the same time. That's highly unusual for major research facilities. Most research facilities will have 1 instrument mounted at a time, and then it's a 10, 15 minute, 30 minute, 2 hour process to move that instrument out of the way and put another instrument on. But because we've got this instrument cube with instruments mounted around the sides, we can, with the simple flip of a mirror, access any side port on that instrument cube and be able to operate multiple instruments in a night with very little downtime in switching instruments. And that's, as I say, pretty unique and pretty special. And that gives us great flexibility so that complicated data products that may involve visible wavelength observations and near infrared wavelength observations can be collected in a single night, and even within a shorter period than that. So we have a lot of agility as a telescope to be able to cater the instrument use to different programs. And it's pretty common these days that 2, 3, or even 4 different science programs are scheduled on a given night. And we're able to do that simply because there's no overhead really in switching instruments. It's just a flip of a mirror, and now all of a sudden you're sending light off to a different instrument and getting the data you need for that. So,
and it's also valuable. And maybe, Matthew, this is something you can speak to. If you have a comet that has suddenly, well, I say suddenly, and not just overnight necessarily, but has appeared, and you typically will study comets with several different instruments, right? They do different things. Maybe you can talk about that a little bit, about how having those instruments almost simultaneously, you can study a comet.
Yeah, absolutely. Well, in fact, you can do simultaneous at some wavelengths. So there's something called a dichroic, which lets, for instance, when we're using NITES, it lets the infrared light go to NITES and the optical light still pass through and go to LMI. So in fact, the project that we all did together, we were getting data completely simultaneously. We were getting images at optical wavelengths with LMI at the same time we were getting infrared spectroscopy. And then also on a given night, again, same project, in 30 seconds or a minute, we flipped that mirror and we switched from getting the infrared spectra to getting optical spectra. And that's just incredibly powerful to have that really short turnaround time that just within an hour, we were on one instrument, got data, went to another instrument, got data, went back to the first instrument and kept getting data. So for comet studies, especially where things are very, they can often change very quickly, or you've got a variety of things you want to do in a short period of time, that sort of flexibility is really powerful.
And that's certainly what makes the LDT so powerful, that adaptability and the ability to change so quickly and look at, collect light and analyze it in different ways. Annika, I wanted to get back to something you had mentioned also. You were talking about part partners, LDT partners. And Nick, maybe you can address this. Just explain what LDT partners are and why, what that means to be involved in LDT. Nick, do you want to take that?
Oh, sure. So LDT, while it's owned and operated by Lowell, we have several partners in the facility that buy in to get access to the facility to do their own science. And so the partners include, and somebody can catch me if I forget somebody, you could forget a partner here, but it's University of Maryland, Toledo University, Boston University, Yale University, and Northern Arizona University. I think that's
I think that's it.
Along with Lowell. So each of those partners have bought into the facility because there's either something specific they want to use, a specific instrument, or they just have a wide range of science that they want to conduct, taking advantage of all these different instruments that are available. And so when we commission a facility instrument, which is what NITES is, there's 3 facility instruments at Lowell. There's NITES, LMI, the visible imager, and Davini, which is a visible wavelength spectrograph. Those 3 facility instruments are on the telescope all the time and are available to any of the partners who want to use it. It also means that we at Lowell have to support those instruments. That means training new observers, teaching them how to use the instrument, helping them process and reduce the data after they've come in, and support in whatever way we can the partner's ability to get the best possible data. And so that's sort of the role of an instrument scientist, I think, is to make sure that your partners are happy, that they're getting what they need to be able to do their science. And to me, that's a really interesting aspect of the instrument project, is being able to see what other people come up with and see what other people are trying to do with the instrument. And that may have nothing to do with small bodies in the solar system, but it's just interesting to see the creative ways that people come up with using their instrument to do their own science.
So you're not a small body snob. You'll pay attention to.
No, I still am.
And when we speak of the partners, as we do this series throughout this year, we're going to have some partner institution astronomers joining us and talking about their research also. So we'll have a nice variety. And in fact, Matthew, if we were doing this, a year or 2 ago, we would have said you're from a partner institution because you were with the University of Maryland.
Right.
So let's talk about asteroids, some of the asteroid work. And first, I want to just go back to NEO's near-Earth objects, because I think that's something that resonates with people because of the potential of disaster on Earth. So let's just talk about those a little bit and what you're able to do with LDT and how that allows us to characterize these things. Maybe, Nick, you can lead off here.
Sure, I can start. I mean, we've all worked on near-Earth objects, and as Matthew said, some of the projects we've done together and published together on our near-Earth object studies. So near-Earth objects, they're objects that come close to the Earth, but because they come close to the Earth, they often have sort of unusual observing circumstances, meaning they may be observable for days or even just a few hours before they whiz by the Earth and then pass off into the direction of the sun, where we can't point at LDT. And so short observing windows is sort of a common issue or a common problem, if you will, that we have to deal with when observing near-Earth objects. And so having the capability to say, okay, here's an object that just came along, I want to get data on it, having that ability to quickly get LDT pointed with the instrument configured and ready to go, sometimes in mere minutes or in very short notice, is an incredibly powerful capability of the facility. So that sort of target of opportunity style observation, where something interesting comes along, you want to be able to point an instrument at it as quickly as possible. LDT enables that. The other aspect of LDT that we haven't talked about much, gets kind of into the detailed operations of the facility, but it's a really kind of unique capability, is asteroids and comets are moving relative to the background stars. They're minor planets, they're orbiting around the sun just like the Earth, and so when we look up at those objects in the night sky, they're moving relative to the distant background stars. And near-Earth objects can sometimes move quite quickly relative to the background stars. And that can be a challenge for telescopes to be able to track at these non-stellar rates. And LDT it performs incredibly in that regard. It's one of the best, we would call it non-sidereal or non-stellar rate tracking facilities in the world, I think. And that means pretty much any asteroid that we discover, whether it's out in the distant parts of the outer solar system or flying by the Earth inside of the geosynchronous satellites, we can track LDT on it and keep the telescope tracking with that object to look like the photons we need to do our science. So that tracking performance of the telescope is really an incredible part of enabling the types of near-Earth object science that we want to be able to do.
This might be a good lead into something you had mentioned before, Nick, and that's the capability of LDT to support missions. Let's talk about missions, and one that you're all involved with, DART, which is a really cool project. So let's talk about that a little bit.
Do you want to say something about that, Matthew?
Sure. So DART is the Double Asteroid Redirection Test. I think I got the name right. I don't always think about what the acronym stands for. But it is a NASA mission which launched last year in November, I believe, and in September of this year is going to intentionally crash into an asteroid. And it's not just any asteroid, it is a binary asteroid. So it's a big asteroid and a little asteroid that's a moon going around it. And they're going to impact on that moon as a test of planetary defense. So the idea is that the collision of the spacecraft into that moon will change the orbital period of the moon as it goes around the asteroid. And by doing that, we will be able to remotely detect the change in that orbital period. And so that's where our involvement has all come into this, in that we have used LDT, among other things, and we are all heavily involved in observing on this to very precisely understand what that period of the moon is and to predict for when the DART gets there, where it will be at the time of the impact, so they can hit it correctly. And then afterwards, we will be observing it again to see how that orbital period has changed. And by doing this, it's going to, it'll be exciting, first off, but it's going to tell NASA and the people who have done a lot of modeling what we would actually take if we had something that was going to hit the Earth, because the asteroid that DART is going to hit is not a threat to Earth. But in the future, if something was a threat and we needed to mitigate it, what would we need to do to prevent it or to shift it enough so it didn't cause major damage? And so this is that first step along that way.
And I think there's a good time to pause for a minute. We've got a couple of pictures we got a couple of questions, and we certainly welcome our viewers to send those in. One question, does LDT get used by the government for any research on NEOs? So
I can take a stab at that. Indirectly, yes. Many of these projects that we're talking about, whether it's DART or our own research projects, they are funded through NASA and the NSF typically. And so those are, federal research funds that help us do the research we want to do. And so, we have various programs that use these grants to observe NEOs and therefore, are sort of falling under the science, the broader science umbrella and objectives of NASA and NSF. As for, government agents in black suits showing up at the LDT and, taking over the telescope, no, that doesn't really happen. It's really just us, carrying out our research programs that may actually have some government funding.
I'm not sure if they could find the telescope dome. It's pretty remote. Well, let's go back to DART specifically. The question, and this is I think we can talk a little bit more about how the public can experience DART. This question, will we be able to see the asteroid impact from Earth? And then on top of that, maybe talk about how people can know what's going on with DART and follow the progress of it. How about back to you, Matthew?
Sure. So the impact, the timing of the impact is not great for us in North America. It's going to be roughly the time zone of South Africa or Israel, and it's going to be over in southern below the equator. So we here in North America would not be able to see the impact. But certainly telescopes in the southern hemisphere will, although again, it's not ideal for where our best observatories are. Keep in mind, though, that even seeing the impact, it likely won't look like much. It's going to be a speck of light that probably gets a little bit brighter. We are hoping that we will see some ejection out of it, so a cone of material. But I've been involved in some of the simulations for this and doing calculations about how bright will it get and over how long. And literally, we're saying we have an answer. It might be off by a factor of 100. And that is not good for planning, for telling people what they might or might not see. So yeah, it will be technically observable by professional telescopes, probably by people with amateur telescopes, but this is not something you could go out in your backyard with binoculars and appreciate something changing.
And this is sort of reminiscent going back to the 1960s with Ranger spacecraft and Surveyor, especially Ranger with the impacts that people with telescopes tried to see if they could detect the impact or see a brightening. It's a similar type thing that it's kind of fun to look at least. But in general, people will be able to watch video after the fact and see simulations about this and everything. Is there a good place for people to watch this, or is it going to be, all over NASA?
So I don't know the direct URL, but it's run by Johns Hopkins University Applied Physics Lab. They have a fantastic site with a lot of outreach type things. I'm sure as it gets closer to NASA social media, we'll be giving you all kinds of links. Annika, Nick, if you've got other ideas on that, please chime in.
No, I think that's, I don't know the URL off the top of my head, but Google, just Google DART mission NASA and you'll find out.
And Johns Hopkins at the APL lab is the same one who launched New Horizons to Pluto for that successful mission. Yeah. Nick, you had mentioned, or maybe Matthew, I did, about binary asteroids, asteroid pairs. And Nick, you were involved in research just recently that was pretty exciting related to that. Let's talk about that a little bit.
Okay, yeah. So, as Matthew said, the target of the DART mission is a binary asteroid. So those are two asteroids in orbit around one another. And that's sort of one of the unique aspects of that asteroid that enables the DART mission. Again, we're trying to change the period of the satellite to see what happens. And that's, Matthew mentioned a factor of 100 in uncertainty about what we're actually going to see. That's the whole point of doing the experiment. We have no idea, and that's kind of cool. It's not often you do an experiment and have zero, not zero, but have little constraint on what actually will happen. And so that's an exciting aspect of it. So that's what we would call a binary asteroid. But there are other objects in the solar system that we find that have been referred to as asteroid pairs. And these have been known for 20-ish years or so. And these are objects that are on very similar orbits around the sun, very similar, but they're not bound to one another like a binary. They're sort of almost flying in formation in a sense around the sun. And so the first question we ask about these objects is, are they just coincidentally close to one another, or are they related in some way? And so that's something we can use LDT to answer. We can look at their composition, and if they have the same composition, well, it's a strong indication that these two objects that look like they're flying in formation may be related. And if we can convincingly argue that they are related to one another, then the question is, how did they get there? How did they end up on this sort of common orbit around the sun? And the sort of best theories available to explain that process suggest that these things were once a single body that have broken into pieces, 2 pieces, maybe more, and that what we're seeing now is the sort of leftover of that breakup process. And recently we've found some of the first of these asteroid pairs in the near-Earth object population. And in those cases, these are likely quite young objects, certainly in geologic terms or solar system timescale terms. The latest one that we published on is an asteroid pair in near Earth space that's probably only about 300 years old. So that's an absolute blink of an eye in astronomical terms. So this is something that, if people were around with big enough telescopes 300 years ago, they may have actually been able to witness the breakup of this asteroid pair. So,
and that's the youngest known pair at this point, right?
Yeah, by a factor of about 100. Yeah, and we continue to find these as discovery surveys are out there scanning the skies, finding new asteroids every night. Interesting things show up, and this one that we studied recently was sort of showed up in my inbox one day, and so we used LDT to study these objects in detail.
Now, it's interesting because over the past several years, it seems like there's been a big increase in the number of known pairs, like Arakoth, the New Horizons saw, paired bodies in general. Is that, I mean, have we really been finding more recently, or is that just my imagination? And is that, and if so, is it because it's the advancing in technology, or why are we seeing more of those?
Yeah, so I mean, part of it is just we're getting really good at discovering new objects, and that's that growth in the number of known asteroids and comets in the solar system is at historic levels, and will continue to increase as new surveys and new technologies come online. So we expect over the next couple of years to have the minor planet catalog, which is about just over 1 million objects we know about in the solar system. That catalog is going to increase by about a factor of 10 over the next couple of years, thanks to next generation surveys that are coming online. So there's a lot of stuff to study out there, and will be keeping us busy. And as that catalog grows, you start to find these weirdos, these things that are unusual and interesting, including these asteroid pairs. You mentioned Arakoth, which is what we would call a contact binary. So that's not like Didymos or the dark target that's in orbit around one another. It's not an asteroid pair in the sense that they're separated. That's two pieces that stuck together and now have this sort of bilobed or peanut shape. And there's interesting questions about how you get one of those and how long that's been around, things like that.
Is there an estimate? Well, there probably is, but what's the estimate now of the number of or percentage of binary systems out there, small bodies?
It's a little bit dependent on where you look in the solar system, but a rough number through at least most of the inner solar system, and Matthew and Annika, you may know better in the outer solar system, but in the inner solar system inside of Jupiter, it's about 15%.
And among comets, it appears to be much higher than that. Between the comets that we visited with spacecraft, so we have pictures up close, and then one comet that came close enough to Earth that we got good radar, we have, I think, 5 out of 8 appear to have this bilobed kind of shape, like a snowman shape. Mm-hmm. So we think that that's very informative of how comets must have formed, that it was probably either slow speed collisions, which caused them to stick together, or some subsequent evolution. There's lots of ideas now about maybe they're collisional and then they kind of reform into preferentially 2 or 3 pieces, which stick back together at low speeds.
Well, since Matthew, you kind of introduced comets a little bit there, let's go and switch over to comets. Something that you're all involved with in one way or another, cometary research. Annika, what kind of research have you done related to comets?
Yeah, so one of the first projects that I was involved with NITES actually was on some close approaching comets. And this was in collaboration with both Matthew and Nick. And so what we wanted to do was, the close approaching comets gave us an opportunity to, as the comet got close enough to Earth, we could actually resolve the comet coma in our images with NITES. And so what that meant was that when we were placing where we were going to observe the comet with the NITES instrument, we could look further out in the coma, we could look over the nucleus, we could look, above and below and to the sides. And so essentially this allowed us to gather information from all parts around the coma and study whether or not we could detect any heterogeneity in the coma. And so if there were more or less dust, if the sizes of the particles near the ejecta were different than they were in other locations, then that could help inform some of the structure that's going on in the coma. And so that's a project I took on near the end of NITES commissioning and the start of NITES science time.
So, and what does that tell you if the composition is changing in different parts of the comet?
Yeah, so we'll expect that as the ejecta, or as the coma, you're moving further from the nucleus out into the edges, that things are going to change. Just as far as particle size goes, if there's water, then it's getting blown back into the tail. And Matthew will say this much more eloquently than I will. But what I was interested in particular is if you're looking near the nucleus, do you see larger, say, chunks of material that are coming out, being ejected from the comet nucleus compared to other locations? And so, that information is informative of what possibly the internal structure could be like, or what the underlying material is like that's different than just what's residing in the outer coma.
I'm going to jump in and elaborate a little bit more. In particular, that LDT is the biggest telescope in the world that is equipped with comet filters. So these are specific filters designed specifically to study comets, to show us particular bits of material, and usually gases. And if I'm remembering the project correctly, Annika, Dave Schleicher and I had gotten data very close to your observations, maybe even the night before, using these specific filters. And so we were able to take our images, turn them around overnight, and tell you exactly where to point, so that you knew if you were in a jet or not in a jet. And so that's the sort of thing that LDT made possible, because it's got this fantastic suite of instruments.
Another thing related to that project was the historic nature of the flybys. I don't know if you want to talk about that. This is not an opportunity that comes along every year or even every decade.
Yeah, the last decade, we've just been incredibly lucky. And I didn't realize it because I was new in my career during that decade, that how infrequently we have close approaching comets. But in the last 10 years, we had like 3 or 4 of the maybe 10 closest approachers in the last 100 years. I don't remember the specific numbers, but I can tell you that there is a dearth of them going forward. So after having this great time, especially while Annika was a grad student, where like every year there was this amazing opportunity, now it's 10, 15 more years before anything comes by that gets anywhere near as close or as bright as what we had then. So we got a lot of fantastic data. In fact, just earlier today, I was talking with Dave Schleicher about research projects we have, and we're sitting on plenty of data we just haven't gotten around to publishing yet, because we had so much in the last 5 or 6 years.
Yeah, I think I got observations of 4 comets within a couple of months. Yeah.
Let's look at something here for a second. I mean, we're talking about asteroids and now comets. And what's the value of studying those to astronomy then beyond?
So I'll start, but I think all 3 of us probably have our own takes on this. With comets, we like to call them the fossils. I like to call them the fossils of the formation of the solar system. So comets are rocky and icy. We call them dirty snowballs, and they have largely lived far enough away from the sun that their ices have remained more or less intact since they formed. So at some point in the recent past, they have been perturbed, and now they're coming in close to the sun, but they haven't been doing that for most of their lifetimes. But when they get close to the sun, they heat up, they're releasing these gases, ice becomes a gas, and we can study what they're made out of. And that's it's giving us a window into what the conditions were like when those comets formed, which is when the planets were forming. So if we want to know how planets formed, we can study comets and learn what they were made out of.
The asteroid answer is very analogous to that. It's just that asteroids formed closer to the sun, so they generally are ice or volatile poor. And so you can think of asteroids as sort of the leftover bits from the terrestrial planets that didn't get incorporated into one of the terrestrial planets, Mercury, Venus, Earth, or Mars. And so by studying those, we study the initial conditions for the terrestrial planets, how they, what material was available for them as they were accreting and building up. And again, because they don't have all the surface geology and weather and atmospheres that planets have, asteroids have remained relatively unaltered in 4.5 billion years. And so they really are kind of a time capsule to not just what conditions were like as the planets were forming 4 billion years ago, but also everything that's sort of been happening in space since then, evolutionary processes like space weathering and collisions and things like that. So they're sort of a witness plate to the beginnings and the subsequent 4 billion years of solar system history.
And for people who don't study astronomy, there's also a practical aspect of, we mentioned about near Earth objects, near Earth asteroids, but the same as with comets, that these things can impact Earth and alter life on Earth. So there's a lot of direct interest for people also, I think. And in fact, we have a couple of questions here that I think we'll take now. This is a good time. Let's take a couple. With current technology, how much warning time do we need to try and divert a dangerous comet or asteroid?
I mean, we'll get a data point from DART in terms of the effectiveness of that particular mitigation strategy. And that mitigation strategy is what we call a kinetic impactor. Smash a spacecraft into an asteroid and see what happens. So we'll get a data point for the first time and how effective that methodology will be. There are many other proposed techniques for diverting asteroids and comets. And really, the techniques you have available to you are dictated by the lead time before impact. So if you have short warning or short lead time before impact, your options are very limited. If you have years or decades, then you have lots of options on the table. And then of course, it's all very size dependent as well. If we're talking about a 50-meter body, that's going to be a very different mitigation strategy than a 500-meter body. And so it's sort of size and lead time dictate what your options are. And we'll learn a lot from the DART experiment to see how effective at least this one approach will be for an object of that size and with that particular mitigation strategy.
Yeah, I'm going to add to that too, Nick, and just say that because of the size of the LDT as well, it places itself in an interesting and unique position where it can help add to discoveries so that we can increase warning time for a lot of these really small objects that cannot be discovered by a lot of the current survey telescopes. And so the LDT is in this niche position where we can add specific data points to better understand what the orbits of these objects are, and so we can better track them so we know if there is going to be a potential impact, when it would be. But of course, as the technology advances and more surveys come online, we'll be learning about more and more objects. So we'll be able to get more advanced warning for a lot of the objects we discover.
Annika, since your vocal cords are warmed up here, here's a question regarding something you had mentioned before. With the comets, when you're looking at the composition, did you find them mostly heterogeneous, or were they more homogeneous, or what did you find?
Yeah, so it was I'll say an interesting experiment, as it was one of the first times we used nights in this way. And so for the most part, the results are looking homogeneous in the sense that we're not detecting any strong changes as we look in different parts of the comet coma. But this is still ongoing, so I'm working to get models so we can place some limits on what the changes are as well by incorporating more of the composition and some of those like grain size information.
Okay. And we actually have several more comet questions, so we'll take these and then talk about a couple other topics. Here's one about the lobed comets. Let me see if I get this right. With the two lobed comets, would the collision take place in the Oort cloud or elsewhere? And what would knock them out of the Oort cloud if that's where they were, to the inner solar system?
Yeah, so most likely it happened before they were placed into the Oort cloud. The Oort cloud is a very sparse environment, so we don't think there are many collisions happening.
Can you define what the Oort cloud is?
Yeah, sorry. So our solar system, the inner solar system, we've got our planets, and they're more or less in the plane of the solar system. Out at the very edge, we've got Pluto, and then the Kuiper belt, which is sort of another belt, like the asteroid belt in the inner part. Kuiper belt's at the outer part. And it gets a little bit more complicated. I'm going to simplify it down, say everything out to about 50 times the distance from the Earth to the sun is roughly in our plane. But then way out beyond that at 1,000 or 10,000 AU, so at AU is, again, the distance from the Earth to the sun, there's more or less a spherical cloud of presumably icy bodies. We've never imaged anything out there. We infer its existence because the orbits of comets either are on short period orbits, which we can trace to being close in, or they seem to come from all directions, but they all get out to about the same distance away, and that's known as the Oort cloud. So out in the Oort cloud, there are very few comets for any given area, so we don't think there are many collisions there. So we think those collisions would have happened when they were forming, which was roughly in the region of sort of like Saturn out to Pluto, the current day positions of Saturn out to Pluto. And that they probably were then kicked out because the giant planets moved around. And so gravitationally, they were kicked out to the Oort cloud. But many of them, and this sort of wraps up with the other part of the question, many of them were ejected completely from the solar system, lost altogether. But those that made it to the Oort cloud stayed out there until some additional gravitational perturbations sent them back in again. And what that is hard to know for any given comet, but we know statistically that happens from, for instance, passing stars. So the sun over millions of years passes relatively close to other stars. That can give comets enough of a kick that they'll come inwards. There may be other things. Maybe there's another planet way out there that's also sending them in, although we've never seen any signature of that in the comet population.
What percentage of comets come into our inner solar system once and then we never see them again?
You know, I hoped you wouldn't ask me that question because I don't have the perfect answer there.
Yeah.
The long-winded answer is that quite a few get lost along the way. Probably 10 get lost for every one that we keep. But of the ones that actually make it in near enough from Earth for us to see them, I think it's fairly high. I guess it's 80, 90%. But like I said, along the way, before they even get to the chance where we see them, that's where we're losing most of them.
Okay. And let's take one more comet question. Here's a good general one. How were comets discovered, and why were Neowise and Leonard and others only discovered months before they became naked eye?
All right, so I'll take this one again, and then I'm going to defer to let others talk. So comets are discovered through surveys largely, the same way that asteroids are. In fact, many comets are discovered first as an asteroid, and it's only upon subsequent observation that we notice that, oh, this thing is kind of fuzzy. And so then it gets called a comet. Comets also get found by amateurs. It's the one area or one particular area that amateurs can still contribute. In particular, because big telescopes like LDT can only point but so close to the sun without risking damaging their optics. But amateurs or sort of unpaid professionals, because there are some really good people who just do this for fun, and they really know what they're doing, and they look close to the sun, and they can find comets that are missed by surveys. And I don't remember the specific scenario for either Neowise or Leonard, but both of those, or from time to time, there is a bright comet that's coming in the general direction of the sun, and so we just can't point telescopes to find them. The other aspect on both of those is that they brighten dramatically between when they were discovered and when they got bright, because they came close to Earth. And that's the way comets work. So if you find a comet that's out, say near Jupiter, a year later, it's going to be close to Earth, and it might be, I'm trying to do quick math in my head, 10,000 times brighter, something like that. So this is not at all uncommon, just the way comets behave.
Okay. Well, we've covered some nice territory with comets and talked about asteroids. We've got a few minutes left, so I think we should talk about, one of these bizarro things, an asteroid that has an orbit like a comet. And all of you have been involved in research on this Phaeton, which is the parent body of the Gemini meteor shower, among other things. So, Annika, what's your involvement been with Phaeton?
Yeah, so I joined the campaign idea, I guess, after Nick and Matthew. So I'm not sure if I'm the right person to start the discussion, but I can certainly talk about my contribution to the campaign after. But they're the ones that organized the campaign.
Okay, Nick, or one of you want to take that?
Sure. So, Phaeton's one of these really weird objects where it was discovered as an asteroid, meaning it didn't have that fuzzy halo around it or coma that Matthew just mentioned. But it shares an orbit with the Geminid meteor shower. So a meteor shower is a stream of particles in space that the Earth plows through every year. And so Phaethon orbits within the Geminid meteor stream. So Phaethon is an asteroid, has a meteor stream. Meteor streams are generally produced by active bodies, comets. They release material, and that material then impacts the Earth when the Earth passes through that stream, and that material appears as meteors. So you've got an asteroid with a meteor stream, and then relatively recently it was discovered that Phaethon has sort of a hiccup every time it comes close to the sun. So it kicks off just a little bit of material, sort of like a puff of dust gets kicked off the surface, and then it's inactive the rest of the time around the sun. And so it's just a weird body. It's neither asteroid nor comet. It's probably a dead comet, you know, maybe once was much more active than it is now. And so there's lots of, you know, interest in this particular oddball. And actually there's a planned space mission to Phaethon by the Japanese Space Agency, a mission called Destiny Plus. And they'll be flying by Phaethon and taking a dust counter and all kinds of interesting instrumentation to look at what's going on with this object and why is it showing the properties that it does. And so Phaethon every now and then has a very favorable observing circumstances. And I think that's what Annika was referring to. The last time it came around, it got quite right. It was quite favorable for observing because it got close to the Earth. And so we sort of marshaled all the LDT resources we could and did an extensive campaign to characterize this object sort of in unprecedented detail, I think. I don't know if you want to talk, Matthew, about some of the stuff that we learned, or at least new questions that were raised by our study of Phaethon.
Sure. Well, one of the things that we did was to do the deepest search that has yet been made to try and find gas around it. So saying, if this is an old comet, or if there's cometary material or activity, this is our best chance to find it. And we didn't. That's the spoiler. We still didn't find anything. We also went looking for fragments that could have just been meters in size because it came so close to Earth. We were able to look for those. Didn't find those either. We did manage to get exquisite, we call a light curve, so a study of how bright it gets over time. And we did it at multiple filters. We did it, I don't think we haven't published on it yet, but we have NIGHTS data and Devaney data, so optical and infrared spectroscopy all the way around as it rotates. So that's just more data for us to play with because we had this fantastic close approach. And it was just a great opportunity to use LDT and its flexibility and for our teams to work together as well.
And that was a really fun night where we were using essentially all three instruments, and it was good we were all there because it was chaotic. Switching between instruments and the efficiency was not something that one person could reasonably manage. We really needed 3-4 of us in the observing room just to be able to deal with the influx of data that was coming in. So it's kind of a unique opportunity there. A very bright target coupled with all the instruments available to study it.
And fortunately, as I recall, it was an evening object, so it also meant we got to bed at a respectable hour.
That's it.
That's convenient. Just a couple of minutes left. One follow-up question. How many asteroids are dead comets? Is there any estimates, or is it just a handful that have been proven so far?
Nick, I think you're best equipped for that, or Annika? I don't know. It's a really good question. I don't know the answer to it. I kind of view, humans like to put things in nice, neat bins. We like to categorize and classify things, but when it comes down to it, it really is a continuum. And, some asteroids are more comet-like and some comets are more asteroid-like, and there's things that fill in the gaps, and Phaethon's definitely one of those objects. And so, how to draw that line and say this is definitively a dead comet or just a slightly active asteroid, it gets hard, and I don't have a great answer for what percentage of them actually, would fall into those categories.
That's what's great about the technology. As we advance, we start, it's just like planets. Everything used to be obvious. It's a planet, moon, asteroid, or comet, but now we have all these gradational things that kind of fall in between because we have better technology and can find smaller things, and that's what makes it so fascinating. It seems like every time you point the telescope up, you answer one question and get 10 more questions to answer. And it's a never-ending process. We have just 2 minutes left. So Matthew, in a minute, let's talk about the interstellar objects, because that's really cool. We want to get to that before we go.
Sure. So the interstellar object he's talking about is Oumuamua, which was the first object ever discovered that clearly originated from outside of our solar system. We know that from its orbit. It was moving too fast to have been gravitationally tied to our own sun. And I will just quickly say that was probably my most exciting observation with LDT, was getting to observe Oumuamua. And what we helped to discover with those observations was that it had this really elongated shape. We didn't actually see the body, we just saw the brightness of it change. And in 45 minutes or an hour, it went from being very bright to, I'm not sure I can even see it in the image anymore. And then 45 minutes later, it was just as bright as it was at the beginning. And so with our data, which we published almost immediately, and the communities, we figured out it must have a very odd shape.
And this kind of goes against what Nick is saying about classification, but what do you call it?
Oh, that one's tough. It is so confusing. It moves, so its orbit gravitationally seemed to have some sort of outgassing that must be happening on it, because it didn't simply follow Keplerian orbit. So it was behaving like a comet, yet we never actually imaged the material coming off of it to tell us it's a comet. So five years on, we are still arguing this out in literature of what explains the phenomena that we observed.
So much more to learn. Well, I think that's a good place to end tonight. This has been a great conversation, and there's so much great research going on with asteroids and comets and other small bodies of the solar system. Annika, Matthew, and Nick, thanks so much for joining us tonight. And thanks to everybody out there for watching. Cody, Jody, and Heather are behind the scenes folks who are making this all work. And we'd also like to thank our members who make programs like this possible. So thanks for joining us tonight as we talked about some of the small body research done with the Lowell Discovery Telescope. And we look forward to talking next time about the LDT's 10th anniversary and the science we're learning from it. Good night.